Hey everyone, welcome to the third lecture of Advanced Topics in Communication Networks. So today we'll kind of like finish the P4 part of the lecture. So you will actually know at least theoretically all that there is to know in P4. Of course, from a practical point of view, you still have a lot to learn, but that's where the exercises are coming from. But let's say from a conceptual point of view, will be done today. And then we'll continue our journey through label switching, and probably we'll start the traffic engineering part. We'll, of course, continue this next week, also starting to see load balancing. And as I told you, we'll use, in traffic engineering, we'll also start to use MPLS. So label switching will be, of course, like one of the building blocks, as I told you, that we'll use in the lecture. So perhaps a quick reminder as well, as you know, you can ask questions through the Zoom chat. Many of you did so already in the previous lectures. So please continue to do so, but you can also ask your question live directly using your voice. So for this, the only thing you need to do is to raise your hand using the corresponding Zoom feature. So if you click on the participant list, there should be in the lower right a raise hand feature. And if you click on it, then we'll see that you have a question. And that's another mean for you to ask a question. So either raise your hand and then we unmute you and then you can ask a question directly. So it's a little bit more human, let's say. Or again, if you have like background noise behind you or for whatever reasons you cannot ask the question directly, of course, feel free to do it as we did last time through Romain. So just use the Zoom chat in this case and then ask your question there. And Romain will just interrupt me every now and then to actually relay the question back to me. All right, so let's go back now to the slides and let's see a little bit, a quick recap of what we saw last week, and then let's jump into the materials of this week. As you will see, it will involve a lot of back and forth between last week and this week's slide, just like to finish the material accordingly. All right, enough chit chat, let's jump right into it. All right, so last week we saw essentially three things. We saw the P4 environment. So beyond the language, what is it that you need to actually code in P4? We started, and we will finish today, to dive into the P4 language, so the different constructs that are available to you. And then we started to look at the label switching aspects. And we looked at this from, let's say, a conceptual point of view first. So from the environment point of view, what we saw, that's kind of like new since P4.16, which is still today the latest iteration of the language, is that we have the concept of an architecture. So as I told you in P4, the idea is that you can code in P4, it's a target independent language. So you can code a P4 program and then run it on a hardware switch, on a net FPGA, on a network interface card in your Linux kernel, or in a software switch. So there are different targets that you can program with the same P4 code. At least that's the idea. And so the way it works in P4 is that there is this target model, which is provided to you that kind of englobes, if you want, the target specific aspect of the device that you are like trying to program in P4. And the P4 architecture is really just an API, so an interface to program this target. And in the lecture, as I told you, what we'll use is a software target. So this is the target that you already have been using in the last 2 weeks, which essentially corresponds to the normal PISA architecture. So you have an input parser, you have a sequence of match action table, a switching phase, and then another sequence of match action table in the egress pipeline, and then the output. So that's like very standard, and essentially the software model kind of maps this architecture perfectly. So this is what we will use in the lecture. As I told you, if you want to play with actual hardware, be it an FPGA or a Tofino switch, you can do so, but then in projects, like semester thesis, master thesis, etc. So that's for like what is, let's say, important to keep in mind for the environment. From a language point of view, what we kind of like started to do is kind of like dissect the different kind of operations we can do in P4, the different type of limitation as well that we can do. That we have because of the language. So another thing that I told you is that you have this concept of metadata. So remember the metadata, these are like this extra packet state that is not really on the packet, but is carried over with the packet as it progresses through the pipeline. And you have like different types of metadata. You can define metadata for like intermediate results, for instance, but you also have metadata that are automatically populated by the switch or by the target that you're actually programming. Depending on the target, you will have different type of metadata that are populated. So independently of the device-specific metadata, though, there are like kind of like standard metadata. And so these are actually kind of like shown on the slide on the left-hand side. These are like metadata that are in the P4 spec, and that any target, being software, hardware, anything, will actually implement the metadata on the left-hand side. Another important concept, and this will be even more important today because we'll actually also speak about stateful construct, stateful object, but it's this concept of extern. So kind of like the idea behind extern and why it actually appeared in the language is that in the previous iteration of the language, so not P4.16, the language before it, so P4.14 in this case, there was no concept of extern. And then what we ended up having in the language is a lot of like, say, target specific aspect that were not nice. And so the idea now is to kind of like abstract away the target specific aspect, put that behind extern, kind of like in interfaces that are kind of hidden from you, and only use them through the interface. So you don't need to know the implementation, you only need to know how to access them. So that's the idea behind this extern. And so that's quite important in P4.16, and that enables also P4.16 to be target independent. Because, for instance, to access the stateful memory, you just go through the interface, and whether it's a software switch or hardware switch, it will be the same call to actually access the memory, even though the implementation of that call will be very different in the backend. All right, so we saw metadata, concept of extern, and then we started to deep dive a little bit into the language. We discussed the base types that there are, and we also saw that there are ways to kind of like combine these base types together to create like composite data structure or data types. And typically you will find these composite data types for headers, like headers or header stack. So that's something you have been playing already in the case of MPLS. So that's what we saw last week, and you started to play already with this construct in the exercises as well. And so something that is kind of like very important in P4 to be aware of are the kind of like limitations on the operations you can do. So you can do, let's say, the basic ones plus minus times. You can do, of course, like bit level operations, so logical operation, bit slicing, bit concatenation. But you cannot do division, you cannot do modulo, you cannot do floating point operations. So essentially, there is a lot of limitation in the language. It's nowhere as powerful, let's say, as C++. Far from it, really. And again, this is on purpose, is because the idea is that, of course, these programs, they have to run very fast, and they have to run in hardware that can run possibly at terabits per second. So you only have a few nanoseconds per packets in order to reach the line rate. So that's kind of like the only way that you, at least today, the only way we can kind of like reach such speed is by restraining the type of operations we can do. And that's why P4 in itself, it's kind of like limited. All right, so today we'll finish this journey. So we'll continue speaking about the match action pipeline parser and the parser. I won't really speak about it because I think you already know what is needed to know, but we'll kind of like speak a little bit more about the pipeline. And we also speak about, as I said, the stateful constructs. So this is kind of important and will be even more important in the next exercises, the ones that are coming up later. So this will enable you to maintain state across multiple packets. So right now, the variables that we have seen, they kind of like are restored every single packet. So here, you will actually be able to maintain a little bit of state. Not much, because again, it is limited, but still better than nothing. And you will see it enables a lot of cool applications. So I will give you a few examples of those as well. All right, so this was for like the P4 aspect of last week. And another thing we started to see is the concept of label switching. And first, from a conceptual point of view. So as I told you, this protocol that we'll see, that you have started to see last week as well, this MPLS protocol for multi-protocol label switching. The intuition here, think about it, is that it's kind of like IP meets virtual circuits. And it's kind of like trying to blend the two together. So IP is a connectionless protocol, virtual circuit is connection-oriented protocol. And kind of like we take a little bit of both and kind of like create a blend, which is, as you will see, very useful and used very much so in practice as well. And the idea, really put it simply, is just to put quote unquote labels on packets. And we actually store this label in between the layer 2 and the layer 3. So in between the link layer and the network layer. So that's why we speak about a 2.5 layer protocol. So as I said, like MPLS relates very much to the concept of virtual circuit. So remember, the idea of a circuit is that instead of like just having packets that are like independently forwarded node by node, you actually have the source that creates an entire circuit in the network. And normally in the old days, these circuits were kind of like physically allocated to you. So it was extremely easy to forward alongside them. So you just create the circuit and then just pipe the data through. Of course, that's not very realistic to do, let's say, in a large network, to actually build physically these connections. So what we go for is for like a slightly relaxed concept of virtual circuit. That's kind of like the idea with MPLS. And so now each link in our network will carry many of these virtual circuits. So a circuit really between the source and the destination, or in our case, more an ingress switch and an egress switch, really to be a little bit more precise. But we really can have many of these connections on the same link. And then we can just play with how we allocate these connections onto the links. So we can be, let's say, very conservative and only allow one connection per link, in which case then we actually can have guarantees. Or we can be kind of like very loose and kind of like go a little bit like best effort, like IP, and then essentially not care really where the connections are going. And so kind of like, then we will degrade into a best effort service. So depending on how we play and how we allocate these circuits and how we map them to the physical topology virtually, then we can kind of like adapt the guarantees we have. As I told you, what we try to do in this lecture is to get better guarantee than best effort, at least for a subset of the traffic, the one we care about the most. And so these kind of like virtual circuits will enable us to do this. So, okay, so it's nice to say that we'll forward based on labels instead of forwarding based on IP address. But for this, we need to figure out, okay, what do these labels look like and what are the operations that are performed on this label across the different devices in the network. And so we saw that the operations, so the label first, I told you, goes in between layer 2 and layer 3. It's a 20-bit label, and you can have actually multiple of those. 20-bit gives you 1 million different values, around 1 million different values to the 20. And essentially the operations you will do on this label in the data plane, so that's kind of like in P4 land if you want, it's either to push, to swap, or to pop. So typically push, you will do that at the entrance of the network. So for instance, on, let me try to do this, if that works, whoops. So on this ingress router over there, we'll actually perform a push. So that essentially will turn, by pushing a label, we turn an IP packet into an MPLS packet. Then the label packet will start to flow in the network. Then we'll have the core label switch router. They will perform swap operation. And I told you, swap operation is kind of like a way to kind of like enable better scalability. So instead of having the same, or mandating the same ID, the same label to be used across the entire network all the time, that would effectively kind of like limit us to 2 to the 20. We can actually switch this label around. And so each have like local device specific label. So that label space. So that enables to have 2 to the 20 per device. And we'll actually, you can actually go even deeper and have 2 to the 20 labels per interface. So that's something we'll see today. So we can actually scale this thing pretty well. And so essentially, if you are in the core of the network, you will perform swap, and then the label packets will switch the labels until they reach the latest router in the network, this one over there. That's the egress router, and there you will perform a POP. And essentially, when you perform a POP, you turn an MPLS packet into an IP packet. So at least if it is the latest label on the stack. That's kind of like the operation you need to keep in mind. So that's important: push, swap, and pop, the three key operations that an MPLS router or MPLS switch. As I said, the notion of a switch and a router in this lecture will be blended together. But essentially, these are the three operations you perform in the data plane when we're talking about MPLS. Of course, there is an entire control plane, and that's something we'll see today, that is also ruling over this switch and essentially tells them what is it that they should use as a label for reaching this destination or that destination. So that's kind of like the idea now of the control plane, which again, you wouldn't implement in P4, you would only implement that in, let's say, Python, C++, Java, and then talk to the P4 program that is running then in the target.
Laurent, we have a
Yes.
first question.
Yep.
We said that we have a 20 bytes for the MPLS labels. Is this
20 bits, yes.
20 bits, sorry. Is that a limit set by the protocol specification, by MPLS, or otherwise what's the reason behind this limitation?
It's a good question. I'm not sure what is the actual reason behind the 20-bit choice and not like, let's say, 32 bits for the label itself. So the entire MPLS header is 32 bits long, and out of these 32 bits, you have 20 that really represents the label. I think it was deemed enough back then for the applications that were considered. So it has been a while that MPLS was actually standardized. Yeah, so I must say it's probably I can look it up. Let me look it up to try to see what if there is really an engineering reason behind that choice of 20 bits, and then I can start with this also next week. But on the top of my head,
follow-up question would be: what are the 12 last bits used for?
Yeah, so there are a few things there. Like one thing is there is a TTL value which is there, like in IP. So that's something we won't really see in the lecture because it's kind of like a detail. But MPLS packets, like IP packets, can actually loop. And so you want a TTL to kind of like prevent, let's say, these packets from being sent forever and ever in the network. So what you can do, which is often done, is like when the IP packet enters into an MPLS network, the router, the ingress router, will actually copy the TTL field of the IP packet into the MPLS TTL field. And so that enables you to kind of like translate the MPLS hops into IP hops as well. So if you perform a trace route, you will actually see the different MPLS router in between as well. There is a way to cheat though, that's also often done in practice, is to actually just use a different TTL value for the MPLS packets that you create than from the IP TTL value. So there is an IP packet, let's say, that arrives, value 64. You kind of like create an MPLS packets by pushing a label on top of it. And then instead of the TTL 64, in the MPLS TTL, you put 255, let's say. Then you decrement the TTL value, and then when the of the MPLS header, and then when the packet leaves, you pop the MPLS header, and then you end up with an IP packet, again with a TTL value of 64. So essentially all the hops in between the network, they are kind of like invisible. It's like they did not happen from an IP point of view. And so that is sometimes used in practice, and that enables actually operators to kind of like hide the internal network. And so this is actually very often the case in virtual private networks. So that's something we'll come back to a little bit later, but essentially that enables kind of like, let's say, Swisscom to kind of like pretend that the entire network is actually a single hop just by like not decrementing the TTL. So TTL is one of these fields that you have in the 12 bits. You also have a couple of bits. I don't remember the exact numbers, but perhaps a byte or so, which is used for QoS marking, so that enables actually to tag the packet as high priority, low priority, medium priority. So you also have this in the MPLS header. And then you have like a bit that serves as an identifier for the bottom of the stack. So that's something you probably have seen as well last week in the exercise session. That enables an MPLS router, an MPLS switch, to actually figure out that this is the last label in the stack. And then the next pop operation you do, you will actually turn it into an IP packet. So these, let's say, are the most important fields that are there beyond the label that you should, let's say, at least know about. But really the most important ones for the lecture are the label itself, of course, and then the bottom of the stack. That's kind of like the two most important ones, and the ones, of course, we'll see in the lecture. So yeah, I hope that answers the question. Any more questions, Romain?
Not for now. Okay,
cool. But please keep them coming. Also, don't hesitate to raise your hand again and ask your question by voice. Otherwise, Romain will continue to read it. Okay, so let's come back now to the slides. I told you about the three operations: push, swap, and pop. So this is very important to understand. Then we have the forwarding table. So that's something we also saw last week. So an MPLS switch uses a different forwarding table for label packet than for IP packet, of course. And so the content of the forwarding table is kind of like given here. You have the label, of course, of the incoming packet. You still have an X stop, live for an IP packet, and you have an operation. So the operation is swap, push, or pop. So this is what we discussed already. And the next stop, typically an outgoing interface, or it could be the router itself. This is typically done when the router, for instance, is the destination of the packet. Or, for instance, that is also something we'll see in this lecture, actually. When you arrive at the very last router, the very last labeled egress router, if that router receives a label packet, it needs actually to kind of like process it twice. So to receive the label packet, look at the label, perform a pop, and then you receive, there is an IP packet that emerges from that pop, and then you need to do a second lookup to actually figure out what to do with that packet, and then actually send it out to the IP next step. That's why it's often the case, to kind of like avoid these two operations on the last router, that the penultimate router, the one just before the last one, will actually perform the pop operation, so that the last egress router, if you wish, actually just has to forward the packet as a normal IP packet, because there is no label anymore. That's kind of like an optimization. But again, it's often done, very often done in practice as well. All right, so this was for brief recap of last week, and already discussed a couple of this week's elements, actually. So this week, we'll finish the P4 language aspect with the stateful construct, finish the label switching, continuing with the demo as well. So I will try to continue playing with my leader routers as well that are running MPLS right now. And then we'll probably start the traffic engineering aspect. So let me switch back to the previous slides of last week and directly jump to the part about the match action pipeline. And the idea here is to talk a little bit more about tables, actions, and control flow. So I will kind of like, I think a lot of these things now, you know them already, but I will just kind of like highlight them so that you also know what is kind of like perhaps a little bit more important to keep in mind for the project, but also for the exercises. Okay, so one thing that, again, you know, I'm sure because you already played with IP lookup and MPLS lookup, but you can have different types of match action in a table. So you can, for instance, match using an exact match, match using a ternary match, or then you have a mask, or match using a longest prefix match. What perhaps you do not know as well is that you can have multiple keys at the same time. So for instance, you can match at the same time the destination address and the version, and you can use different match kind for each as well. So just to show you that it's perhaps a little bit more powerful than what you had in mind initially. So For instance, something that you could do with this, even though it's not part of the specification, but you could, for instance, match at the same time on the MPLS label and the IP destination address, which is contained, let's say, underneath. So you could, for instance, do that for whatever application. It doesn't really matter. It's just something that P4 would allow you to do. And again, that's something that none of the routers out there, being from Cisco, Juniper, Brocade, or the routers, Nokia, all of them actually don't allow you to do this. It's kind of like hard-coded. So that shows you just, if you were ever to want to do this, you could actually do it with P4 very easily, really. Okay. So I told you this already, exact ternary longest prefix match. That's the one, the three kind of like match action you will play in this lecture. You also have the range match action. So here, as the name indicates, you can just check whether a value is in a given range. Order architecture can provide you with other type of matches, but as I said, we'll only play with the software targets. So these are the ones that you should know about and be able to use. Something which is, again, very important to keep in mind, but I think by now it should be clear in your head, is that the table entries are added by the control plane. So you define the table in P4, you define the key, what the action should be, all that is defined in P4, but the actual content of the table, this is defined by the control plane. And there is an API for that, which is automatically generated when you actually compile the program. That's just an example here of two table hats that are done in the IPv4 longest prefix match table. Okay, actions, we already talked about that. I will be brief. Essentially blocks of statements that can modify packets. What is something you perhaps you have seen that I'm guessing in the exercises, but perhaps you didn't pay too much attention to that, is that if you look at an action, it actually takes directional parameter. And so here, so when you have like an action and a parameter block, let's say like 3 parameters that the action takes as input, you actually need to indicate kind of like whether the parameter that you give will be used only as input, only as output, or both. And that's actually why we do this, or why P4 does that, is that it actually gives more hints, if you want, to the compiler to reason about the semantic at a high level, to reason about the semantic of your action. And it's actually very useful for extern, because then the compiler can actually reason about how the parameter that you give to an extern function will be modified, even though it doesn't know anything about the implementation of the extern, which is really target specific. That's kind of like something that P4 mandates you to do in order to ease the job for the compiler, really. So it's kind of like the reason behind this. You have to do this. So as I said, 3 types of directions, pretty intuitive, I think, in, out, and in, out. So in means that the parameter you give will only be read inside the action. It will never appear on the left-hand side of an equal sign, for instance, so you will never modify the variable. Out is kind of like the opposite. It is uninitialized when it arrives. When you call the function, there is nothing there, or like arbitrary value, and then it will actually be written into by the action itself. So think of like return values. So these are typically the return values. And in out is kind of like a combination of both. So it's something that you care about, the values that enters, you care about it, and then you will rewrite it as well. And then you care also about the out value of it. So, so if we, for instance, like re-illustrate this by an example, so that's, I think, the example you had in the first lecture, which is a simple packet reflector. So the packet arrives, and then we just bounce it back on the same port. And here you can see now, and I guess you can, let me illustrate this here, but you can see the parameters. Now you see this in-out kind of like modifiers that are added to it. And you can see that the source and destination MAC, so these 2 parameters, we actually have to put them as in-out because we care about the incoming value, because we actually need to read that, but we also need to rewrite them accordingly. That's why we need them to be in-out. On the other end, the input port, we don't need to rewrite it because anyway, it wouldn't make any sense. There is an input port on which a packet arrives and that's it. So there is no need to rewrite this, but we care about the value. Likewise, the output port, it's not defined yet, but we care about it, of course, a lot because that's where the packet will actually go. So that's kind of like the intuition. So you have to think about, okay, what is it that I want to do with my parameter? Of course, oftentimes it's actually easier to reason about this without you can actually write down your program without the directional modifiers, so without the in and the out. And then you can see, okay, this is how I'm using that variable. This should be an in-out one. This one should be an in. This other one should be an out. So that's kind of like perhaps a little bit easier to apprehend if you do it after the fact. But you need to add these modifiers in order, again, to help the compiler. So like visually, this kind of like looks like this. So if you think about the reflect packet here as this box, and again, you can consider then the action as a black box or as a gray box here. The in-out care about the value entering and leaving. The in, it only enters, but it doesn't leave, and out, it only leaves, it does not enter. Again, like these are kind of like perhaps peculiarities of the language, but I think they're important to understand, otherwise it may look too abstract and you don't really know what you are doing. Okay, and yeah, and another detail here is that the parameters that come from the control plane, they do not take a direction. So again, this is I understand this is a little bit intricate, but essentially the parameters that pertain to the data plane aspect, they take a directional parameter, a directional modifier, not the ones that come from the control plane. So typically, actions that come from the results from table lookup, they will not take directional parameter. Again, I think if you, as you start to do exercises more and more, these things will come automatically to you. Okay, about the control flow, a few more details about how you can interact with tables. So that's perhaps something important to keep in mind, but I told you, right, in this ingress and egress pipeline, you can have multiple tables in a row. And this is actually very useful. So oftentimes you will see this. So typically, for instance, you will have a table perhaps where you perform, let's say, a match on the layer 2 addresses, another table where you perform a match on layer 3 fields, and then yet another one where you perform a match on the transport, let's say, header, layer 4. So these tables, they will come in sequence. And what you can do is kind of like link their logic semantically. So you can kind of like adapt what you do in table 2 according to what has happened in table 1. And something else you can do that enables you to actually link them together, for instance, is that the packet arrives, you make the lookup in table 1, and the action of table 1 modifies the metadata of the packet. Remember the metadata that are carried over with the packet as you progress through the pipeline. And so table 1 modifies the metadata, and then you match on these metadata in table 2. So that's, again, like showing you how to link these different tables together and how they can talk to each other, if you wish, through this metadata that is carried over with the packet. So that's kind of like what is illustrated here as well on the slide, is that in order to implement this logic, you kind of like need to know whether the table was hit, whether kind of like there was anything that matched in the previous table. And sometimes you also need to know what was the action that was run on it, whether it's an IPv4 forward, an IPv6 forward, etc. Because perhaps it will depend what you do in the next table accordingly. So here, this is how you can do that. There is these commands, how you apply a table and check whether the table has been hit or which action has been run. So that's kind of like important. And this, you will use that in the exercises. Probably you even have used that already. All right, another kind of like perhaps extra important things regarding control flow is to reason about checksums. So all these P4 program, very often, right, they start to modify the packet headers in some way. Actually, even if you think about it, like a normal router, not a P4 one, it modifies the TTL field. So you actually need to re-update the checksum because you have updated the header. So you need to recompute the checksum that applies on the header, of course. And so the same goes when you are like playing with the headers, like changing like the address field or like adding new header fields. So you need to update the checksum accordingly. And so in P4, you have like dedicated function to do that. You have, of course, a function to verify the checksum. So that's nice to do, of course, to make sure that the packets you receive has not been corrupted. And then you also have functions to update the checksum. And as I said, it's very important to do that whenever you start to modify the header. And so here you can see that, for instance, like the update checksum function. So you give a condition that needs to apply for the update checksum to actually take action, to be executed. Then you give the data on which the set of fields, if you want, on which the checksum has to be computed. Source IP, dest IP, source port, destination port. Where the checksum needs to be written into the header. So for instance, in the IP header, there's a checksum field. That's the field you would put. Then which algorithm you want to use to perform this checksum. So you kind of like need to indicate all of these in P4 to actually exactly tell the switch what to do. And so, for instance, this is an example here, which oftentimes you can really copy and paste because it's if you're playing with IP headers, you will use it as is. So you, of course, the precondition is that you want an IP header to be there and to be valid, and then the field list, is all the fields in the header that on which the checksum needs to be applied. So version, version, total length, ID, flags, etc., TTL. All these, the checksum, actually, if you look in the IP spec, the checksum is computing on all of them, on the entire IP header. So you need to actually indicate all of them. You write the results of the checksum. Oops. You write the result of the checksum in the checksum field. And then in this case, we use csum16 as the checksum function. Of course, you could imagine create a new protocol with P4. It's very easy that uses a different way to compute checksum, or perhaps don't even do checksumming at all. So again, this is something now that you can do. Okay, so there are more advanced stuff. I've kind of like skip a bunch of interesting things, but you should check them out yourself, and also during the exercise you will actually play with them. But something, of course, which can be very useful is the ability to clone packets. So you can kind of like multiply packets and create copies of a packet. You can also recirculate packets. So that's also very useful. Sometimes you have the packet that arrives, you do a little bit of processing. For instance, you modify the header, then you can resend the packet back to the beginning of the pipeline and then reprocess it as a new packet, for instance. So that is very useful when you are hitting the limit of the switch, for instance, and you want to perform more operations than what you can normally do with one pass in the pipeline. So that's typically used in this situation. Then you will send the packet once, perform, let's say, a third of the operations you want to do, recirculate the packet, perform the second third, and the last third in the third recirculation. And here you would just modify a bit, for instance, or like 2 bits that indicate in, for instance, if you are like in round 1, 2, or 3 of, let's say, the processing. And accordingly, in your P4 code, you will just modify the instructions that you do on the packet. So that's, again, like a way to kind of like gives you a little bit more expressivity, if you want. Of course, I must say that there is like a performance penalty, as I'm sure you understand, that you kind of like, by doing this, of course, the processing time increases. And if you think about the hardware target, you're also using up kind of like throughput internally in the switch, because you actually need the packets to come back to the beginning of the pipeline. So in the switch, what is actually going on, hardware switch, is that there is a dedicated port, which is an internal port that is not seen on the face of the switch, which is used to actually bring the packet back to the beginning. So it's really like kind of 100 gig port, for instance, that is used to recirculate the packets. So you can go up to 100 gig of like recirculation. After that, you will have congestion there as well. So again, like this is something I believe you will use in your project, for instance, if you want to do fancy things, and also perhaps in the exercise. And a third thing that is important to keep in mind is actually the second on the slide, is that you can also send a packet to the control plane. And so that is also very useful. For instance, when you are like, let's say you code in P4 and you would like your controller, which is rolling over the network, to, for instance, be aware of, let's say, some of the packets, perhaps that have some significance, special significance for you. So what you can do is kind of like, either you create a new clone of an existing packet and you send that one to the controller, or you can even send existing packet to the controller as well. And then you can do whatever you want with the controller. So that's again like something which is quite useful, especially when you start to build hybrid application that combine software and hardware together. So this is again something you need to think about, but at least you, whether you can use it in your, let's say, project or exercises, but just know that this is definitely possible to do. Yeah. All right, so yeah, so quickly here, just to give you another example of an interesting P4 code that uses two tables. So I mentioned this a little bit before, but here the example is about performing layer 3 forwarding, so IP-based forwarding with two tables, hierarchical table. The cool thing by doing this, instead of doing it in one table, of course you don't need two tables in practice, but you can. And this gives you a layer of indirection that enables you, for instance, to enable fast convergence. So that is something that we'll use, for instance, and we'll talk again when we'll see fast convergence in a couple of weeks. But here the idea is that when packets are entering the router, in this case, because we are talking about layer 3 forwarding, you will put the packet in the first table, and the first table will actually map the IP packets with, let's say, an index. And this index will be put in the metadata, will be carried over with the packet, and will be sent to the second table. So the index is here, for instance. Let's say there is a packet that arrives. The destination is 1111. So this first entry will hit, and then the metadata 1 will be added on top. And this will go, actually, this will not go here. This will go to the second table. And in the second table doesn't care at all about the IP prefix anymore. It only cares about this index that you have put here. And so if the index is 1, you go to 10. If the index is 2, you go to port 12. 3, you go to port 30. So why would you want to do that? What is the advantage of doing so? Well, just think, for instance, about this use case in which you have perhaps a router with like two exit ports. So 3 interfaces in total. Traffic enters on interface, let's say 0, and then leaves on interface 1 as a primary path, primary next stop. And then there is a backup on interface 2. So a cool thing you can do with this hierarchical table is to map all the prefixes to either 1 or 2. And by doing so, if there is one of the link that fails, you can just update a single entry, so the entry that maps the value to port 1 or port 2 in the second table, and then reroute the entire traffic in a single update. If you had a flat table, and that's why these things are very useful in convergence, if you had a flat table with, let's say, 700,000 IP prefixes, prefix 1 goes to port 1, prefix 2 goes to port 1, 700,000 times, you will need to update every single entry in order for the traffic to be rerouted. Again, like those of you who know about communication networks, the first lecture, I mean, that we had together, we talked a little bit about that in this case, adding a level of indirection enables you to be more flexible. And in this case, it enables you to converge much, much faster. So this is why, for instance, you would want to do this. So the way you do that in P4, let me come back to the slides, and I will finish with this example, and then we'll do the break, is that you essentially define two tables. A table in which you do the IPv4 lookup, and then another table in which you perform the forward action. Of course, the IPv4 lookup, you perform it on the destination address, that's the key. And then the action is to set the next stop index or to drop if there is no match. And then here you will just forward according to the next stop index. And you can see, of course, the size of the table should be adapted to how many prefixes you have and how many ports you have as well. And so, for instance, here, so that's how you would define the two tables. And this is how you actually stuck them together. This is what I was telling you by using this, this kind of like apply a statement. You can actually apply only the second table forward if the first table has been hit. So essentially what is going on is that the packet arrives, you check whether it's an IPv4 packet. If it is an IPv4 packet, you apply the IPv4 longest prefix match table by using the apply function. You check whether there is a hit. If there is a hit, you know that the metadata has been set, and then you apply the forward table as a consequence of that. And if not, right, if these conditions are false, then the packet will just be dropped. And that's okay, of course, depending on the semantic of your application. All right, okay. So actually, I can just like go quickly through this because the parser, really, there is nothing much more interesting than what you already know with this emit function and the fact that you must not forget to emit any fields that you have, extra fields that you want to appear on the packet, and of course the fields that you have like used and modified. So it's just like more like a reminder, but typically the deparser code is pretty static, so you don't change that frequently. Just if you add a header, of course, you need to think about emitting it back. All right, so let's do the break here until 3:15, and then we'll continue with the stateful construct and then the end of label switching. So, and also feel free, of course, to ask questions, and we start again at 3:15. All right, welcome back. I hope you can hear me. You should, yes. So let us continue now. I will quickly finish actually the P4 part, talking about the stateful constructs. That's really the last thing in the P4 language. And then you can only use P4 in the rest of the lecture, but you won't need to know, let's say, any other concept at least. This we'll do quickly now, and after I will quickly go through the end of the label switching. Reasonably speaking, I think the traffic engineering part probably won't have the time to go, but perhaps only the beginning. For those of you who are confused about the slides, I'm actually using the slides from last week. I was using the slides from last week, and now we'll switch back to the slides of this week. To talk about the stateful construct. So this will be the slide right there. So there are slides numbered now, by the way. So this will be slide 23, and we'll start from there. And then I will switch back to last week to finish the label switching part. So I'm sorry about this back and forth, but that's why perhaps you don't see exactly the same thing as the slide deck, of course, which is online. All right. So. Also something that might be useful for me to know, you can just put that on Slack, perhaps even at the end of the lecture, but don't hesitate to let me know if the lecture is dead slow, so you're bored to death because I'm so slow, or it's way too fast and you cannot kind of like keep up with it, or like anywhere in between, because of course, since I cannot see you, it's hard for me to know where I'm standing, whether I'm on one end or on the complete opposite. So like a little bit of feedback I would definitely appreciate. So feel free to tell me this after the lecture, for instance. All right, so now let's switch back to the material. So as I said, I will switch to the slide of this week. So I'm talking about this week on advanced topics in communication network. And now we'll talk about the stateful construct. So how do you maintain state in P4 across packets? Very important. So essentially, there are like kind of like 4 ways to maintain state in P4. You can use tables. That's kind of like one way to maintain state across packets. I mean, the table content is maintained across packets, right? But that one is a kind of like easy. That's the one we already know. So we won't really talk about it anymore. There are 3 other ways that kind of like you should know about. The first one is register. The second one is a counter. And then the last one is a meter. So all of them are stateful, meaning the switch actively maintains state across packets for each of them. And they're actually used differently for different applications, but also the way you kind of like the way the controller can access them or interact with them, or the switch itself changes. So it's kind of important to know the differences so that you can use them the best in your application. So that's what we will see now. And first, I want to speak about the register. So it's probably the one that you will use one of the most when it comes to stateful construct besides stable. And as the name indicates, a register is just kind of like a tiny blob of memory that can contain some arbitrary data. And small amount, because as I said, we are talking about very constrained hardware. So, so typically what you should think about is like you have, let's say, dozens of megabytes of memory that you can use, for instance, for these registers or like for other things. And then that's it. There is no more memory in the device, for instance. So it's very limited. You cannot start like storing huge amount of data. Still, as I said, you can do interesting things with that. So register is a way to kind of like access this memory. And you define a type. So essentially, you define what you want to store in these registers. For instance, I don't know, 32 bits, 64 bits value. You define this. You have to define this at compilation time in your code. And then you have a write and read function to access those. And what is a little bit, perhaps a little bit more specific is that to P4, I mean, is that you actually allocate these registers in arrays. And that's just because of the kind of application we built in networking. Typically requires to have more than one register. For instance, you might have one register that you associate for each of the flow that you are seeing through the switch, or like each of the port, or each of the IP address. So you see that you kind of like need more than one registers, and that's why you have this concept of array. So essentially, the way you define a register is like this. You will have, of course, the register instruction, then you define the type. So what you want to store in the registers, like 32 bits, for instance, values, how many entries you want, and then the name of the register. And then you have this write and read command. The write command takes an index and the value that you want to write at the index. And the read takes the variable that you want to store what you read in, and then the index that you want to read. So this is kind of like how you interact with these registers. So it's really quite basic if you think about it, but it really helps. So you can actually build quite interesting application with this extremely simple construct. So let me actually give you a few examples right now. So one thing that you can do, which is something that we will use even in the coming weeks, is, for instance, to calculate the inter-packet gap. So the time that is elapsed between two packets, let's say, of the same flow. So that's kind of interesting, for instance, because you might remember that because of TCP, for instance, traffic tends to be bursty. So TCP connections, like the sender, they tend to send a lot of packets, then they have to stop, wait for some acts, and then send more packets after. That leads to kind of like a bursty behavior in which you have train of packet, nothing, train of packet, nothing, etc. So by computing the gap between packets, you can actually very easily figure out whether you are in one of the train, because the gap is very tiny, or you are in between trains, because the gap is large. And then one thing you could do is adapt, for instance, the way you forward the traffic accordingly. So one thing you can do is that whenever you are within a train, for instance, so during a burst, you don't adapt the path because you don't want to start to have reordering, because packets you start sending take another path, which might be faster. And so arrives before, because you might remember that TCP does not like reordering. But if you are in between gaps, you can actually then safely modify the path, because the next burst will arrive a little bit later, and that will leave enough time for the packets that are already sent to actually make it to the destination. That's kind of like one typical application of why you would like to use this inter-packet gap, for instance. So the way to do that is actually to use a register. So timestamp in P4 also on hardware targets, they are like typically expressed in 48 bits. So you define like a register with 48 bits. Define a size. So in this case, we decided for 16K entries. So again, this is up to you to put whatever size you want. Of course, there's a price to pay, right? The more you put there in a hardware target, the more memory you use. And so it's not useful to actually put too much there, because then you might actually not be able to compile your program on the given hardware target. So less is better, but of course you need enough for your application to work at all. And then it's kind of like super easy semantic here. What you do is that you define an intermediate variable that happens to be the value that you stored before in the register. So it's the last timestamp of the previous packet in that flow. So here I'm using a flow ID as an index in this table. And you could just think that flow IDs, for instance, is a hash computed over the 5 tuple in the TCP header. So sorry, IP and TCP header. So typically this is what you will do. So you read this, you store that into last packet timestamp, and then you compute the interval. So you do the current timestamp of the existing packet minus the one of the previous one. That gives you the interval, and that's what you write then back into the register. So that's in a nutshell how you would actually calculate the inter-packet gap in P4. So I hope you see that it's actually quite easy. Another example of an application, which is also very common, it's a stateful firewall. So oftentimes, especially in companies, but also at home, you actually want your host within your network to, of course, establish connections with hosts on the internet. So for instance, you want your smartphone to be able to access, I don't know, WhatsApp, Netflix, etc. But on the other end, you don't want, let's say, sources on the internet to be able to establish connection with your devices without your device initiating them. And so that's the idea behind, one of the ideas behind the stateful firewall is to only allow new connections from your internal network. And so why you need state in order to kind of like implement this application? Well, you need state because the packets that are coming from the internet, let's say from Netflix, WhatsApp, or from an attacker, you need to be able to distinguish whether they belong to a connection that was initiated from one of your devices before. So that's kind of like why you actually need this, this kind of like state to be maintained. You don't need much state though. So for each connection that you create, you just want to remember with 1 bit, for instance. So you can have a register with a single bit, an array of register with single bits, that the connection was indeed created by one of your devices. And if the return packet happens to match this, then you allow, otherwise you drop. So that's really, in a nutshell, that's the stateful firewall application. And that's exactly what we have implemented here. So as I said, the idea is that the TCP packets arrives, you check whether they are coming from interior or the exterior. If they are coming from the interior, if it is a SYN flag, you add the flow to the register, otherwise you forward. And of course, you also forward the SYN packet out. And then the return packet that comes from the internet, they will not be from the internal network. You check whether they belong to you check the register. If they match, you allow, otherwise you drop. And so this is actually how you would implement this in P4. So as I said, you can just use an array with single bits, just to remember whether you have seen the flow or not. So this is like a non-flows array. And then essentially you have like 2 blocks in your control flow. One that is applied if the packets come from, let's say, ingress port 1. Let's say you have like port 1 is your interior network and port 2 is the internet. So if the packet comes from port 1 and is a SYN, you write into the register. If the packet comes from port 2, it's, oops, it's not very precise, sorry. If the packet comes from port 2, then you actually check the register, and if the flow is known, then you allow the packet, otherwise you drop. That's kind of like how you would implement such an application in P4. As you can see, it's quite easy. Okay, there are a few lines of code, of course, but it's not like very hard to reason about, and it actually implements something very useful in this case. So that was the first stateful construct, registers. So that's the most general one as well. And the next 2 that we'll see are more specific. So they are dedicated to specific application. First one is counter, and we'll use it to count. And the second one is meter, and we'll use to measure rates with it. So let's talk first about counters. So counters, as I said, they are used for counting, as the name indicates. And you could use a register for counting, really. So it's just that counters are dedicated dedicated entries for counting. So if you want the usage of a register is generic, while the usage of a counter is specific. So it allows also from a hardware design point of view to optimize the counter logic a little bit better. So whenever you want to count, it's a little bit better to use counters, but they come with one drawback that I will mention. So one thing important to know, of course, is how you actually access them. And there is this count methods or instruction. And as for like the register, there is also a type here. The type is a little bit different though than before. There are essentially three things you can count in P4. You can count the number of packets that you have seen, the number of bytes, and the number of packets and bytes. So both combined. So it's not like a size that you give like 32 bits. You essentially tell the switch, I want to count the packets, I want to count the bytes, or both. And essentially all then the kind of like the packets will flow through your pipeline, and then you associate them with a counter, right? And then all the packets that hit this counter will increase and increment the counter accordingly. So here, something that I want to stress is that you don't have a read. You can count in P4, but you cannot read in the switch. That's kind of like one important difference with a register. So a register, you could write and read, like for instance, how we computed the inter-packet gap. In a counter, you can only count, the switch counts as the packet flows, but the switch cannot read these counters. Only the control plane can read the counters. Of course, the control plane can pull the counters and see what's the value of these counters, but the switch itself does not know and cannot know how many packets have been matched or how many packets have been counted so far. So if you need this functionality, then you must use a register because otherwise you cannot read that. But if it is just, for instance, to maintain statistics and you want the controller every now and then to pull the statistics to figure out what are the flows, for instance, that are seeing the most packets or bytes, then you can actually use a counter. It's very appropriate for this. So that's something kind of like important to keep in mind is how do you access the value that has been stored and which entity can access the value that has been stored. As for registers though, counters are assigned in arrays. So same reason, oftentimes you really want to count for many different let's say, entity you want to count for, like all the flows, all the ports, all the prefixes. So you typically allocate them in arrays. Of course, the array can have only a single entry if you don't care about storing more than one thing. So you define your counter. You have a size, like for instance, 512 here values. You define the type and then the name of the counter. And then essentially you can start using it with the count instruction. And here, for instance, by using as an index the ingress port, essentially I'm counting, for instance, the amount of traffic that each port has received. So every time the apply will be like executed, there will be a count that will be affected. There will be a count that will be affected, and the index will be the ingress port. So effectively, I will start to count the traffic that that each port has seen, for instance. If you were to use a flow ID or an IP prefix ID, you would then start to count all the flows, all the prefixes. I guess that's intuitive. As I said, the control plane reads this. So there is a counter read, as you can see, that returns like the value of the counter right now. So that's something that you can do from the control plane only. And an interesting thing, which is quite useful actually, is this kind of like notion of direct counter. So think of this as a kind of like syntactic sugar, really, that enables you to automatically attach one counter to each of the entry to a table, So that enables you to kind of like very quickly, without having to define all these counters one by one, you can, or like an array one by one, you can actually just ask the table to count automatically for you. So these are like direct counters. And so in the table definition, you can actually have a value. There is a counters instruction that you can define point at an array there. And so that's, So I'm getting confused here. So let me backtrack. So direct counters, as I said, this is used to count all the entries that are attached to a table. So you will have like the controller that will start populating entries for a table, and then you can automatically tell the switch whenever there is a new entry, there is a new counter that will be attached to that entry, and the controller can pull them. So that's the way you do that is in the table definition here. Let me illustrate this with an arrow over there. You can see that there is this counter kind of like parameter, and then you can define, you can point to it to a direct counter that you have named. There is no value of the size here, as you can see. Why? Because it depends on the entries that are populated by the control plane. That's why I was confused before. You don't need to define the size of the array here, it's just the size of the table. So essentially, that's the difference. Direct counters, they're like just like defined, the size of the direct counters are defined by the size of the table, which is a function of what the control plane does. All right. Yeah, oh, sorry. Yeah.
We have a question on the counters. What is the rationale for not allowing the reads from the data plane?
Yeah,
why would we want that?
Yeah, so the rationale is again to, it's just as an optimization. It's kind of like engineering, if you want. It's an engineering decision that made all its way into the language itself. So counters, they're really used in practice for like essentially statistics. So statistic-like applications. So like a controller pulling every now and then a counter value, figuring out what are the biggest flows, for instance, and then adapting the traffic accordingly. That kind of applications. So by doing this, by kind of like not forcing the data plane to be able to read this counter's value, when you design the hardware to do that, it's actually much simpler because you don't need to actually wire this memory zone to all the possible stages that you have in the ingress pipeline and egress pipeline. So it enables you to actually optimize your hardware design because it's a restricted interface. So it's easier to implement. The registers, on the other end, you need to be able to read and write them in the data plane in any possible tables. So the packet arrives, there is this ingress pipeline, egress pipeline, and in any table you can start to access and modify these registers. That means, again, from a hardware point of view, you need to wire this table into the memory zone so that they can access the memory. So it's really kind of like this idea. A lot of applications in networking don't require the data plane to access the memory. It's okay for the controller only to access the memory, pulling these things every now and then. And so it's kind of like an optimization. As I said, you could just not use counters and then only use registers, but it's less optimized. So that's kind of like the reason why that was made that way. Yeah.
Okay. Another question related to counters is, do they overflow at some point or they can count up to infinity?
No, of course, they will overflow at some point, yes. So they cannot count to infinity, so they will overflow. Yeah.
Can we pick the size of those counters, or is this something fixed or given by the language itself?
This I do not know. I don't remember at least. Okay. Any TA in the exercise session will know this, so I will just spun towards them. But yeah, I don't know. I think so, but I'm not sure how exactly.
Okay, that's all for now.
Okay, yeah, thanks. Okay, so let me then jump into the last type of stateful construct, which are meters. So meters are used for rate limiting. So they enable you to kind of like compute, they enable the switch, because it's a stateful construct that the switch maintains, to compute the rate. And then according to this rate, you essentially let the switch do something with it. And it's kind of like very restricted the way it is implemented right now. But so essentially you define a meter and think of this meter as an entity in the switch that will color packets. And the packet will enter into the meter, and according to their rate, they will be colored as green, orange, or yellow, and then red. And so the intuition is that you define the rate at which the switch should start coloring in red or orange or green. And so that enables you, by playing with this rate, to figure out whether the packets were exceeding the rate that you set on that. So effectively, that enables you to reason about, let's say, the amount of throughput currently that the switch is seeing and whether it is exceeding perhaps some values that you wanted to see initially. So that's kind of like the idea behind meters. So you have these three colors, red, green, and yellow. And effectively, you need to define the rates at which, as I said, at which the switch will start to color the packets in these three colors. So you define this through the controller. There is, again, an interface to do that. So it's kind of like configured by the controller. And then the meter kind of like executes itself into the data plane. So as for like registers, as for counters, you have an array of meter. Again, same idea. You often need to, let's say, apply meters for all the ports, all the flows, all the prefixes. You kind of like, that's why they come in an array. And then really the only thing you do is you execute a meter. So essentially by executing a meter, you instruct the switch to update the rate that corresponds to that meter entity. And that's it. And then the switch will automatically color the packet. It will be put in a metadata. And you can tell the switch which metadata it should actually write this color into. And then later on, for instance, in the next table, you can start to do if actions, for instance, if conditions, according to the value, whether the packet is red. So red, yellow, and green, by the way, they will be turned into 0, 1, 2, for instance. So that's kind of like how you will recognize this. And so essentially, through the control plane, you configure the rates. The switch, you instruct to execute the meters on the packet that you want. So you control the packets that go through these meters. And then you kind of like, in the next tables, you can kind of like match on the color of the packet. That's kind of like how that works. So for instance, here, just to give you like an example, let's say you want to use this for rate limiting. Of course, that's one of the main applications of these meters. That's actually something you will not use this week, but next week in the exercise. The way you would do it is that you would create an array of meters. And let's say here, I think we rate limit on the source MAC address basis. You can see this here, actually over there. So here, what we do, there is a first table that maps the MAC address to a counter ID. Then we have an array of all these MAC address to the meter ID, sorry. Then we have an array of all these meters, and then we just execute them, and then according to the colors, we drop on it. So that's kind of like how it works. And so, as I said, you define your meter here. There is also a type, packets, bytes, by the way. You can, so it's the same thing as a counter. You execute it, and then you say, you give also, you can see here, the tag of the, sorry, the metadata in which the colors should be written into. So you give the index that needs to be executed, and then you give the metadata that will contain the output color. And then you can, according to this color, for instance, you can start to do something. You can filter. So you can say, if the color is green, I let it go. If the color is red, I drop, for instance. That would be what you would do in table filter, for instance. All right, so that's for meters. As for counters, you have also this notion of direct meters. So again, like kind of like a syntactic sugar that enables you to attach meters to all the entries in the table, in which case you kind of like don't need to indicate the size of this meter array. It kind of like varies according to the amount of entries you have in the table, which again is populated by the control plane. And in addition to the counter parameter in the table, you also have the meter parameter, which is right there, that you can use to indicate which meter should be used for that table. Same thing, very, I think, practical. So likely you will use this direct meter for the same reason as direct counter. So here a summary, again, like of the different stateful constructs. What is important to know, again, is like registers, very generic, can be accessed from the control plane and the data plane. Counters and meters, quite specific in their usage, and can, at least for counters, can only be read by the control plane, and of course can be written by the data plane. And for meters, it's kind of like very even more, well, not more restricted, but it's kind of like restricted in different ways that you count over time, so you compute the rate, and you kind of like execute them, compute the color, and then according to this color, you do something. So that's kind of like the summary on this slide. You can see the data plane interface and the control plane interface to these different stateful construct. And so again, like depending on your application, you need to use one or the other. All right, so with this, I'm finally done with the P4 aspect. So now we are done with the language. You folks should know, at least in principle, all the important parts of P4. That enables us finally now to start like seeing more, let's say, networking, let's say, concept that you can, of course, implement in P4. You started to do that already. But we'll continue now to see this kind of like, remember these 5, 6 techniques. We'll start to deep dive into that now. And again, I'm running a little bit late, so we'll probably only continue label switching today. That's okay, because the exercise is actually, you don't need to know the traffic engineering part for not that much, because it's only the beginning. It's intuitive enough that you can directly go through the exercise session. And next week, of course, we continue with traffic engineering. So now we'll switch back to last week's slides again on pertaining to label switching. So let me switch back to the slides and switching back now to the slides of last week. And starting with slides 124 in the PDF, by the way. Okay, so this is the where we left the recap as well. So we have the content of the label forwarding table. So remember, we are playing with labels now. So we are thinking about a network in which we have kind of like trying to blend IPs and labels together. And we left with the content of this label forwarding table, we have a label entering, a next stop, and then operation, swap, push, up, up. So something I mentioned at the beginning of the lecture is that you can kind of like manage this label space that you have. So 2 to the 20, that's kind of like the size of the label part of the MPLS headers. So you have 2 to the 20 distinct headers or distinct labels. And you can kind of like allocate them if you want to your circuits differently. So one way would be to say, I want my label to have a network-wide meaning. So this effectively means that you have like 2 to the 20, so it's a little bit more than 1 million different circuits you can build in your network. That's not too much if you think about it. So depending on how you build or for what you build these circuits, so if you build circuit, let's say on a per connection basis, on a per TCP connection basis, I wouldn't recommend you to do that, but let's say you want to do this for whatever applications, you would quickly run out of labels for those. So effectively, you typically don't do that. Instead, you will kind of like particularize the label space on a per label router, label switch router, or even on a per interface. So that's kind of like what is said here on the slides. So if you think about like a label switch router and the label for that router, you could imagine having different label space per interface, or having one label space for the entire router. And so the difference is essentially whether you get 2 to the 20 times the number of interfaces, or if you only, quote unquote, get 2 to the 20 distinct labels for the label switch router. But here again, I'm stressing that we are not considering a network-wide allocation anymore. We are allowing swap. And now we are just thinking about whether we allocate the labels on a per interface basis, on a per router basis. So you can see, of course, one key difference is that if you are like doing the allocation on a per interface basis, then in the matching part of the table, you need also to match on the interface. Because essentially what you are allowing the switch to do is to reuse, let me switch back to the video. You are allowing the switch to reuse the label, same label on different interfaces. So in order for the switch to kind of like demultiplex these labels that may be the same, you also need to match on the incoming port. Very easy to do in P4, as you know, right? So there is this ingress port, which is kind of populated, standard metadata populated by the switch automatically. You can kind of like just match on this and the label, and then boom, you have like a per interface now label space. Of course, you're not forced to do that. You can just throw away the ingress port, only match on the label itself, and then you have like a per device label space. That's kind of like the idea. I think it's intuitive, but it's again like design choices that may matter to you or not. A very important notion in MPLS is the notion of a label switch pass, or LSP. So it's kind of like a unidirectional tunnel between two routers. So essentially, it is just kind of like, if you want, a sequence of labels starting from the inbound router, the ingress router, all the way to the egress router. And you can see here on this slide, there are kind of like two LSP that are defined. There is the red one that starts in L1 here and goes to L0. And then there is the blue one that starts in L3 and ends in L2. And you can see that IP packets are entering this LSP, they turn into MPLS packets, and then they leave as IP packets. And in between, there are MPLS packets. The label of the forwarding table are given there. It's pretty intuitive. I think you can, pretty sure you understand this by now. So that's kind of like just that. You have like LSP, so it's kind of like a terminology if you want. Important in the MPLS domain to know that, okay, an LSP is just a label switch pass between an ingress router and an egress one. Yes, so that's kind of like important notion. What is also important to know in MPLS is this concept of LSP hierarchy. So you can kind of like define LSPs that are larger or aggregate of other LSPs. So that's here what is going on. You can see in this part here of the slide, you can see that there is a larger LSP that was created here, and that kind of like combines the two smaller LSP, blue and red, here into one. And the way you implement these things is by actually using it's by using a stack. So you actually use this this capability you have to actually slap labels on top of each other to actually create this hierarchy. And so that's kind of like what we'll see now. And so that enables to actually scale very well when you are like kind of, you can merge many tunnels into one. And then you have only the core routers that need to know about these big tunnels, and they don't need to know about all the tinier ones. And then you expand them after. That's kind of, let's see how it works with this concept of label stack. So let me switch back to the slide and show you this directly. So the stack, that's something you have seen last week. Essentially, MPLS headers can be put on top of each other and then form a stack. That's why we actually do this push-pop operation. Swap meaning just you actually change the top label. So it's kind of like a pop followed by a push, if you think about it. So it's really like push and pop are really the most fundamental operations. And there is this kind of like, as I mentioned, and that was one of your questions as well, this bottom of the stack bits that indicates whether this particular label is the last one or whether there is another one coming after. So if you have this, what you can do is starting to build like hierarchical LSPs. Here, just an example of how it works. I think it's pretty clear. By the way, it's pretty easy to see. For instance, here you see the forwarding table of L3. A label arrives, let's say the red one here with label L3 on top of the stack. You look label L3, you swap with L0. So you see that it leaves here. We are, let me illustrate this here. So it enters there. We look here, we swap with L0, and then we end up here. So that's kind of like easy. Perhaps one which is important, more important here to stress is this one. So here you see that L6, when it's entering into the label switch, the next step is local, and then you pop. So essentially that means that this is kind of like this recirculation business as was mentioning before in P4 as well. So L6 arrives, the next stop is local, meaning that the switch will reprocess it, and before doing so will pop. So L6 will disappear because it will be popped, and then L3 will be reprocessed based on this value. And so that will be the same thing as before. The second label is L3, and then it will be swapped for L0. And you can see that this label packet here will be turned into this one. So L6 is removed, L3 is swapped for L0 and goes here. And that's kind of like what is going on in this slide, which is perhaps a little bit less obvious than all the others, but essentially, I think it's pretty clear. Otherwise, what is the semantic of these things? And here you can see that also L9 is turned into a stack of 2 labels, which is also possible to do. So here you actually have L9, which is swapped for L8, and then another label is pushed after L4. That's kind of like what is going on there. All right, so this is for data plane operation. And now that you have stack of labels, you can actually aggregate red and blue. So this is, again, like what is going on here. You can see here we're looking at L6. It only has 1 entry in this label forwarding table now with an in label of L1. And so here what you do at the ingress switch, L3 and L1, you kind of like push a stack of 2 labels with L1 being the outer label, and then L0 and L5 being the inner labels. So L1 kind of like enables to aggregate now the 2 LSP together because they will share the same outer label. And so L6 only needs to look at the outer label. And the only thing it does, it pops it. And then L7 will see, because of the pop, will see the 2 inner label, L0 and L5. Observe here, that was not done in the slide, but we could have built this kind of like hierarchical LSP all the way to L4. So we could have done this instead, and also enable L7 to only look at the outer label. So here we kind of like, we have broken the hierarchical LSP 1 hop before. But essentially that's up to you to decide where you want to break the LSP, at least when you're looking at a P4 application that does that. Okay, I hope it's clear. Perhaps any question there?
Not so far.
Okay, good. So let me continue then. Okay, so LSP is super important notion to keep in mind when you're talking about MPLS. LSP can be stacked into larger one using this label stack. Another important notion, forwarding equivalence stack. Forwarding equivalence class, or FEC. So that's kind of like the notion which is used at the entrance of an LSP, so the entrance of a tunnel, and enables to map IP packets into an LSP. So you will have your MPLS networks that thinks in terms of labels, and then you have IP packets that enter. So you need to do a mapping between the two, and that's why you actually need this forwarding equivalence class notion. So what does it mean? Well, think of a FEC as just a set of packets that should be forwarded in the same way. And so there are different ways to define and introduce this FEC. One, which is very common, is to actually group all the packets that will exit through the same egress router. So think about your network again. Perhaps you have like, let's say 100 routers at the border, and then you have like the core. So the packets will enter, IP packets enter. You do an IP lookup to figure out where is the egress router that needs to be used. Then you look at what is the LSP I can use to reach that egress router, slap the label on it, and then send the packet as an MPLS packet. The packet goes into the network. The core routers, they only need to care about, okay, the outer label, which goes to the egress. They don't need even to know what is the IP packet for. And then the MPLS packets arrive at the egress, and then you pop, and then you forward out as an IP packet. So very often you will use for instance, the egress router as a forwarding equivalence class. Another example of a forwarding equivalence class is an IP prefix. Very often you also see this, that all the IP prefixes you have, for instance, advertised in your intra-domain routing protocol, like via SPF, will be one FEC. So that means that all the IPs, let's say for prefix 1, there will be an LSP that will be created for those, and then they will be mapped to that LSP. Prefix 2, prefix 3, different LSPs for each of them. So of course, you tend to have many more prefixes than you have like egress routers. So that will lead to more MPLS tunnels. But essentially, this is the same idea, is that all these IP packets have something in common. They belong to the same destination prefix, so they will be forwarded in the same way. You choose, though, depending again on like the application, you will pick the kind of like FEC that makes sense to you. So that is kind of like just a generic notion of essentially a mapping between IP world to MPLS world. Okay, so that's kind of like the idea. So again, like I know it's a lot of terminology, but this is kind of like important to know also, so that you can start reasoning about it. But just like think about this as a mapping and a way to map IP to MPLS. So here, for instance, yeah, question, sorry.
We have a quick question. Can the switch do simply nothing and forward the label as it comes without pop, swap, or push?
Okay. I don't think so. I think if you want, I mean, you can implement the same semantic as you said, but you will swap the label for the same value. But so really, like the three operations you do is push, pop, and swap. So it has to be one of these three. And if you want just the packet to carry the same label as the inbound one, you will swap with the same label, which is done. That is done, but the switch itself is doing a swap internally. Yeah. It's not faster actually. It's like whenever you can do the swap at line rate, it doesn't change anything anymore. I mean, you don't gain any speed, for instance, by not doing a swap. Yeah.
Thanks.
Any other questions?
Not now.
Okay, good. All right. So to finish the lecture, I would just like to give you here an example of this forwarding equivalence class allocation. So what you can see on the slide is essentially three, or in this case, two ingress router. You have RA and RB, and you have three LSPs that have been defined: the blue, the black, and the red. And essentially, what these ingress routers are using as a way as a FEC notion is actually all the prefixes that belong to the same egress router will be mapped to the same LSP. So if you look here, for instance, in RC, you have two prefixes attached to it. You have 12/8 and you have 192.163.13.1, let's say, /32. So these two prefixes will be mapped. They belong to one forwarding equivalence class, one FEC, and they will be mapped to one LSP, in this case, LSP1. So you can see here that the ingress router RA will have in its mapping table, it will map these two prefixes to the same LSP. That means that L2 over there, it doesn't need to know about these two prefixes anymore. It actually only knows about the LSP, in this case, the blue LSP. So that enables to actually scale quite well the inner core of your network, because they only need to know essentially how to reach the edge of your network. They don't need to know about all the possible destinations that you can carry. So that's something that we'll actually do next week and finish next week. So let me conclude the lecture. So again, it took me more time than what I thought, but we made good progress because now really the P4 part is out of the way, and I'm actually quite, let's say, advancing the MPLS part. So next week, for sure, we finish MPLS and we start to dive into traffic engineering. So in the end, it's actually almost on track time-wise. And for traffic engineering, we'll first look at IP-based traffic engineering, in which there is no MPLS. We see the limitations of this. And then, of course, we'll look at MPLS-based traffic engineering. In the exercise session that will start in a few minutes, you will actually start to implement an MPLS-based traffic engineering solution. And it's okay, not, as I said, not to have seen the theory part so much, because you will see it's actually doing allocation of LSPs and then do the mapping yourself. So it's actually quite intuitive, I think, and you can directly go straight to the exercise. In the exercise, though, you will use the MPLS data plane that you have built. So it's kind of important, if you haven't done so, to finish it before. You can use the beginning of the exercise for doing that, and then move on with the traffic engineering beginning of the exercise. as I said, if you have any feedback, please feel free to reach out either through the chat or by email. And with this, I will talk to you next week. And have a nice afternoon and enjoy the exercise session. Thanks.